My name is Nick Colella. I manage the Materials and Characterization core here in the SEC, and I'm going to be talking about some of the instruments that we have and using kind of a demo of characterizing some polymers to show you what the instruments are capable of. So my background's in polymer science, so I love talking about polymers. So this is the only real polymer heavy slide in terms of structures. So for those of you who have organic chemistry background, we produce about 500 million tons of polymer per year. Most of them are polyolefins made from oil. You can see all those in the top left. So the chairs you're sitting on, the coating on the floor, the coatings on the windows, everything around you is coated in polymers. And polymers are part of modern life in many, many regards. Additionally, we are made of polymers. We're made of amino acids, which form proteins and DNA and RNA. So all of those are polymers as well. And we get a lot of bio work done in this lab, looking at different hydrogels, proteins, et cetera. So I treat kind of everything as a polymer and talk about the polymer physics behind it, whether it's biological or synthetic. And also my PhD work was in conjugated polymers used for electronics. So I have to include those up in the top right. So you can see that's from Dow Chemical, how a lot of polymers are made. And then we could talk about biological polymers. And mechanical properties of biological polymers are essential for their function. So you think down to cells, we were looking at the AFM the other day, 100 Pascal, very soft hydrogel. All the way up to collagen is a very stiff polymer. And we can span that gamut. And depending on your application and what biological systems you're targeting, it can be organs in your body, it can be cells, et cetera, you'll need to match the mechanical properties of the materials you're making with the mechanical properties of whatever biological material you want to interact with. So we've learned a lot recently in the past 20 years about cell differentiation and how that is dictated by actually the mechanical properties of the substrate. So cancer cells are very stiff. We can basically find where cancer cells are by looking at stiffness. And yeah, we can do a lot just looking at the mechanical properties alone and then go into chemical characterization as well. So this talk is designed to be an exploration of all the different tools that we have, or at least many of the different tools that we have in the lab here. So I'm going to use a demo to kind of show some differences, and we're going to characterize these two rubber balls. So can I have a good-natured volunteer? Come on down. All right, so we're going to play a game. So we have two rubber balls, and whoever can bounce it off the floor without hitting the ceiling, whichever one gets higher wins. Okay. And I will go first. Okay. All right. Okay. All right, your turn. You've been bamboozled. Thank you. Thanks for being a good sport. So I'm going to pass these around. So these actually have about the same, what we'd call Young's modulus. So they're about the same stiffness. So if you squeeze them, they feel more or less the same. We are also biological, obviously. So we can tell just from our sensory that one feels slightly different than the other. But if you put these in a universal tester, an instron, which is very common in traditional mechanical properties analysis, they'd say they're basically the same material. But we're going to show via all the tools in the lab that they are not. So you can pass those around, you can bounce them off the table, et cetera. And we'll figure out kind of what gives them their properties and why they behave the way they do. So we're going to start off with some chemical characterization, actually. So we have an FTIR in the lab. We heard a little bit about this last week from Arthur. We have Raman spectroscopy and FTIR spectroscopy, and they give very similar information, but in very different ways. So the FTIR is up at the top there. We have our traditional Leonard-Jones potential, and we can model kind of the spacing between two atoms in a bond just with a harmonic oscillator, and we find these evenly spaced energy levels, and that's what we're probing when we're doing FTIR spectroscopy. So we're shining in enough light to promote one level, one vibrational mode, or one vibrational energy level within that mode. And from that, we can tell what bonds are present. So we're going to do that with these two materials. A little bit more about how the FTIR works. So it's an interferometric measurement. which means that we shine in a bunch of infrared wavelengths at once, and then we'll use a moving mirror to, in conjunction with a Fourier transform, to pull apart which frequencies get absorbed and which just pass through the sample or bounce off the sample without being absorbed by any of those chemical bonds. So you can see up in the top right there, many different frequencies coming in, and you see where it says time. That's the signal that the detector gets, and then we'll pull that out. We'll do a Fourier transform to get the actual spectrum. So an FTIR spectrum will look, here's a little bit about the instrument. Let me mute both PCs here. Oh, that one I can't mute, but that's fine. You may hear my emails go off. So this is the FTIR spectrometer, and just a little bit of a picture on the inside. These are all pretty complex instruments. So you see we have the detector in the top left, the source just above it, and a bunch of mirrors. Interesting, all of the lenses inside the system are made of salt crystals, so they will dissolve if too much water gets in the system. And that's because silicon will absorb that infrared light. But we typically work just off this little disc right here. This is the ATR crystal. Ours is made out of diamond in this lab. And you'll place your sample just on that crystal, and then you'll get a spectrum. That spectrum, and we'll go to the spectrum first. We'll come back to analysis in a moment. That spectrum might look something like this. So we have wave number along the bottom. That is the energy of light that's being absorbed. And each peak will correspond to a different vibrational mode. So a different bond or a different kind of a larger mode we might see as well. After we have the spectrum, we're going to process it, which we'll see in a minute, and then we'll assign the peaks based off what bonds are present. So if we have light atoms like hydrogen, it's going to vibrate at a high energy. So that's going to be on the left here. So all the OH, NH, CH all end up towards the left of the spectrum. If we have heavier atoms, they're going to end up more towards the right. We have a lower energy of vibration. Very useful for looking at proteins is we can look at the carbonyl stretch, which is right in the middle, has all these. And that's a very sensitive stretch. So depending on what's around that bond, so if you have an alpha helix versus a beta sheet, et cetera, we can often figure out what's going on in terms of the protein structure by looking just at that carbonyl bond and the exact location of it, that exact energy of vibration. Yeah. And please stop me if you have any questions at any point. We'll take questions at the end as well, but if you see something you're like, hey, what's that? Raise your hand. So this is a raw spectrum, but we need to do some processing on it because this is a little messy. So first we'll do a baseline subtraction and then clean up the spectrum with ATR correction for the crystal. And then we get something that looks like this, which we can process a little bit more easily. So this is the spectrum for what's called the happy ball, which is the one that bounces. So I'm going to use happy ball and sad ball as the terminology. Happy ball bounces, sad ball does not bounce. Whether one is better than the other, we'll talk more about that after. Maybe the sad ball has more applications, we'll discuss. So this is the happy ball spectrum. We can label the peaks, and then we would go ahead and assign those peaks. So a few in here. So we have some CH bonds that we see present here, and they're mostly kind of at the lower energy. If they were a little bit higher, that might mean we have some aromatic groups, some alkenes. We have kind of a general OH stretch, and then we have some stuff in what's called the fingerprint region down below. We can assign those peaks, but it's more difficult too. So this we say, okay, always around here, CH, easy. Those, we don't know if it's a CC, a CO, et cetera. We call it the fingerprint region because it will always be the same, but it's hard to interpret. Not impossible, but just more challenging. And then the sad ball looks like this. So these look very similar to my eye. So there's a few differences we can start to pull out, but we can use some software to help us. So we can take the difference between the two, and we get our different spectrum will look like this. And we see a slightly shift to higher energies here between the sad ball for the sad ball, and we see a few extra peaks show up in the fingerprint region. So that's our first hint that something different is going on chemically with these two materials. So we're going to leave that there for now. So that's FTIR spectroscopy, and then we'll move into optical profilometry. So optical profilometry is also an interferometric measurement. So like we had this convoluted spectrum under time in the top right, we can get a convoluted spectrum like that, but in 2D now. And we get something that's called a moire pattern using white light. So that's going to look like this down here. And we don't have to interpret this as is. We have all the processing with the instrument and the software to do that for us. So the purpose of optical profilometry is to look at a surface. So if you have a surface of a polymer, a surface, I've looked at teeth, polymers, semiconductors, wafers, anything that you might want to know the topography of. And you can get a very large area, so millimeters or more, with high resolution in the Z direction. If you want to know kind of what the surface looks like, optical profilometry is a great technique for that. A little bit about how the instrument works in the top right. So this is what's called a Morau interferometer because the mirrors inside the objectives. And we're going to shine light just on the top of your sample. We look at the light that gets reflected back up into the objective. And then from that, we get our moire pattern, and then we get a height profile. So the height profile can be for anything from, again, precision engineering on metal parts, MEMS, sensors. We get lots of orthopedic, teeth, anything biological that you might want to interface with a body. Tribology, which is kind of wear on a system. Semiconductors, so we can look at traces and patterns of things that have some height topography on the top of a wafer. And also optics, if you have a lens that you want to look at, something like that. Or a mirror, you can look for imperfections in your mirror. Optical profilometry is a great way to do all of those. Anytime you have a surface, the main limitation of optical profilometry is the lateral resolution. So it's a optical measurement. So the best lateral resolution we can get is about 0.5 micron. If you need higher resolution than that, we go to AFM. But for anything that is kind of a larger scale feature laterally, this is a great, easy, fast technique to scan large areas quickly. This is what the software looks like for the optical profilometer. We want that interference pattern to show up on the region of interest. We're going to choose our settings, kind of the range that we're going to scan over in terms of heights. We need to make sure the objective is perfectly normal, so we get light reflected straight back up. Yeah, that's just what the interface looks like for the software. So this is the data that we get for the happy ball and the sad ball. So right now you can see it's curved and we can kind of characterize the curvature, but that's basically just how the ball was made. So we can find the radius of curvature, things like that, but that's not especially interesting in this particular case. We want to know kind of what's happening right on that surface. So we can do a correction to subtract out that curvature and then flatten the image. So this is for the happy ball. You can see the curved image on the right, and then we can remove all that curvature and then take a detailed look at that surface. And this is the data that we end up getting for the happy ball and the sad ball after removing the curvature. So we see some different functionality there, some different types of topography. In particular, for the happy ball, we see it's mostly flat with a few large bumps, where for the sad ball, we see kind of consistent noise and we see some kind of fibers or fibrils, something along those lines, across the whole surface. So very different topography. So we need to think, is that where our mechanical properties are coming from? Probably not, but it gives us a hint about how the polymer was processed and how it likes to assemble. So we can do some cool 3D images. So this can be great for publications and presentations if you want to kind of impress people with all the data you can collect from a surface, depending on what your material is. We can get some nice 3D representations. And you see that if for the curved surface, we can actually start to pull out all that patterning. And for the happy ball, it's pretty smooth still. But we do see those spikes down here.
Quick question.
Oh, sorry. Thank you.
Now a quick question. So like, what's the like color gradient represents? Like on the sad ball, it's like much brighter and like it's like a little bit of orange, but like happy is like mostly orange.
Yes.
What does that really represent?
Yeah, great question. So that is the automatic Z scale. So if we go back here, it's the same as the scale bar here. So don't read too much into that the sad ball is brighter here. It's just because of how it was scaled. The really tall parts are basically clipping the Z scale on the happy ball. So there's spikes that we see down here. Would be the bright part, but it's just very small on that surface, where this one, we don't have those spikes, so the Z scale doesn't get scaled quite as strongly.
Got it. Thank you.
You're welcome. Other questions? Yeah.
So a lot of the samples that I work with are clear or they're very reflective.
Yes. Yeah, great question. So reflective is great because this is relying on that reflected light, and clear is generally fine as well. So we just need some light to be able to bounce off the surface. So basically anything that has more light reflection than like Vanta Black that's going to absorb super strongly, we can get some good data for. One small caveat for that, it can be crystals or very thin films. If they have some nonlinear optical properties, like, you can make a film and then, okay, your wafer looks different now from different angles. For very thin samples like that and some single crystals, then that can cause some weird optical effects, and then the optical profilometer can have some issues. But for most kind of amorphous materials, non-crystalline or thicker films, this works well. You're welcome. Any other questions right now? We can look at statistics. So oftentimes you'll want to know, kind of do some quantitative work. These are nice pictures, but it's not a lot of data just from the image itself. So we want to go and do some analysis on it. We can see the RMS roughness, and we find that the RMS roughness of the happy ball is actually higher than the sad ball. Even though the sad ball has all that patterning, it's very consistent. So we get a very narrow distribution of roughness. For the happy ball, because of those spikes, we can see the kurtosis in particular in the skew. There's a characterization of spikes. We get higher RMS roughness, higher skew, higher kurtosis, means that we have actually kind of a rougher surface for that happy ball, even though when we look at it, it looks smoother. So that's optical profilometry, looking at the surfaces. We can do TGA, thermogravimetric analysis. So this is a great tool if you're trying to characterize degradation of a compound and kind of its degradation profile. It's also very good if you're trying to find solvent content of a sample. What the TGA is basically a really nice balance with a really nice oven. So we have very nice control of temperature, and we have very exact control of mass. So the balance is accurate to 0.1 micrograms, and the max temp on the system is 1,000 degrees, and we have very good control up to 1,000 degrees. So we'll heat up a sample and look at how it degrades and look at how the mass gets lost. So heating can, again, cause degradation. It can cause evaporation. So if you want to, you can burn off organic content and leave the inorganic content. So if you have, say, inorganic nanoparticles in organic matrix, you can burn off the organic matrix, see how much mass is left behind, and that's the percentage that was organic to begin with. So it's a really nice way to quantify composition if you have a mixture of materials. We also can connect this to the FTIR. So you can say, okay, we're evolving some gases. What are those gases as you heat it up? We can send that gas through the FTIR, and then we can get a chemical signature for those. A little bit about the internals of the TGA. So this is the fancy balance inside. So in here, let's see. So there's actually a reference pan in here, and it's a traditional balance, 2 arms. So we have our sample pan here. You'd load typically about 5 milligrams of sample in, and then heat it up. This is the inside of the furnace, nice quartz liner. Yeah. Pan's made of platinum, so it's more expensive, but that's what allows us to heat up to 1,000 degrees. Platinum's a very stable metal thermally. So this is typical TGA data. So this is for the happy ball. Zoom covering it up the label at the top here. Close that. So this is the TGA data for the happy ball, and we see basically 2 or 3 decomposition steps. So we see as we heat up to 600 degrees, how much mass do we lose? At 170, we have 99% of the weight still. So that tells us that we have very low water content, right? Which is what we'd expect, but good to confirm. We don't have any solvents in there. We're just getting a little bit of degradation of the polymer first, and we see a big spike. The first blue curve, that is the degradation curve, kind of slopes down all the way, leaves about 30% residual mass. The second curve on here is just the derivative of the first curve, which helps us see the rate of mass loss, which can be helpful for kind of analyzing the data more closely. So we see around 325, we really start to get a lot of degradation. Then we see kind of 2 decomposition steps. So that also gives us a hint about the chemical functionality that's inside the polymer. So we might have something that has some material that can be burned off very easily, and then there's some residual material, some other material that's left over that burns off more slowly and doesn't really burn off till we're above 400 degrees. So comparing the curves for the happy ball and the sad ball, we see, I missed my sad ball curve. So the sad ball starts to degrade much more quickly, starts at 200 degrees or so, and then we get a slow decomposition profile. So that gives us another hint that these are different materials that we're working with. So comparing the curves, we can see the onset is kind of similar. We see a slow degradation here, but the sad ball degrades much more quickly at lower temperatures. And then they both kind of end up at the same spot. So after we've done TGA and looked at the stability, we can look at kind of what happens before it starts to degrade with the DSC, differential scanning calorimeter. DSC is great for looking at polymers in particular, but can also be looked at proteins, including proteins in solution. If you want to look at how your protein degrades at what temperature, we can do that pretty readily. Can be used for ionic liquids, liquid crystals, anything where you think there's going to be some change in conformation upon heating before degradation or cooling. We can look at crystallization and melting via the DSC. The limitations on this, we can only go up to 550 degrees, so most organic materials are going to degrade well before that, and we can cool down to -90. So we can look at, if you have something that's liquid at room temperature, we can look at how it crystallizes, exactly what is the crystallization point, and then heating back up, what's the melting temperature. These are other types of measurements that we can do. Heat capacity, if you want to know heat capacity of a liquid, that's another common measurement. Purity, crystallinity, we can do this under air to look at how your material degrades in the presence of air. And there's also modulated DSC, which is just kind of a fancier way of doing the rest of these. You get slightly more accurate data. So to actually run the DSC, we're going to load your sample into a little aluminum pan like this. Again, about 5 milligrams of material is generally good. We're going to seal up the pan. We can either seal all the way around the edge, or we can leave it kind of exposed to the environment so solvents can evaporate depending on what your sample is. And so it's DSC, differential scanning calorimetry. The D is for differential because we're going to have an empty pan on one post and then a pan with your sample on the other post. And the measurement is how much more energy do we need to put into your sample to keep it at the same temperature as an empty pan. So all that energy is going into your sample. It can be, if you have to melt something, you need to pour in even more energy. And we can look at the heat capacity as a function of temperature as well. The S is for scanning because we're scanning our temperature, and it's calorimetry because we're putting in energy measuring temperature. This is a little bit from TA about why this DSC is really good, is because they have lots of corrections built in. So we get very accurate data pretty easily using the DSC. So this is a typical DSC curve. This is for the happy ball. So we start at room temperature, and we're going to heat, and then we'll get a melting peak around 60, 75. Onset is 69, and then we cool back down. We don't see any transitions until we get down to -70, and we see this is a glass transition, and we heat back up and we see the glass transition again. So glass transition in a polymer. So a glassy polymer is a polymer that's hard, more or less. We have physical crosslinks that prevent the chains from sliding past each other. So a ping pong ball is a good example of a glassy polymer. It'll spring together and spring back when you bounce it off the ground. A rubbery polymer will also bounce back, as we see. But we have this other rubber that doesn't bounce. So it's neither glassy nor rubbery. That's our first hint. So we see the glass transition is at -60, which means it's rubbery above that temperature. So we see for the rubber ball, it's a rubber ball, and it's bouncy, it's rubbery. Interestingly, we don't see the melting on the second curve, and we don't see any crystallization here. And so does anyone have any guess as to why we do 2 heating cycles, a cooling cycle in between? So this is standard for DSC. We'll do a heat, cool, heat. Why do we need a second heating cycle? Yeah.
I'm just gonna guess, let's say like you heat it up and it deforms, so you need to cool it down to go back to its, I guess, again, is that why?
That's very close. So you're right in that once we heat it up enough, it will lose its thermal history. So it can deform, it can melt, etc. We can melt crystallites, we can go through a glass transition temperature. We're basically erasing the thermal history. So when you prepare a sample, you can drop cast it, you can solvent cast it, in other ways spin coating. You could lyophilize it, you can freeze dry it, you can drop it into liquid nitrogen. There's a variety of ways of creating a solid film from a liquid to begin with. That's going to have some thermal history. The first heating cycle is going to reveal that thermal history, and then we're going to heat to erase it, then cool it down and heat it again. And we've effectively erased the thermal history. So now the second curve is just characteristic of that polymer. It's not about how you processed it. It's just for the material itself. So we see here, we have some crystallites that formed when this rubber ball was formed. And then we see this onset of melting right around 70 degrees. On the second curve, we've erased those crystallites. We've melted them and they didn't recrystallize on our slow cooling. So we've done some characterization and some modification of the system. So anytime you take what that ball is made of, the second heating cycle should always look like this. The first heating cycle can look different depending on how that sample is formed. So that's why we generally do heat, cool, heat on DSC.
What
For the
happens?
sad ball, we have a little bit more of an interesting curve here. So again, the blue curve is the first heating cycle. We see kind of a broad melting type transition starting at about 33 degrees. We cool down, we see kind of a broad crystallization like starting again at 63 degrees. And then we see our TG starts to be around 11 or negative 12 degrees. And then we again see the melting. So this one actually does recrystallize and we get some new melting upon the second heating cycle. So very different from what we saw for the happy ball. So again, more hints that we have working with different materials. The TG here is very extreme and you can see there's a change in the heat capacity. This is an even trickier question. Any ideas why we have a change in heat capacity when we go from a rubbery polymer to a glassy polymer? Or vice versa. So when we have a glassy polymer, these chains are all, there's not a lot of volume, free volume that's available in the system, so the chains can't slide past each other. They're kind of locked in place by those physical crosslinks. Squeeze together, squeeze back, bounces like a ping pong ball. In the rubbery state, we have more free volume. We have more energy in the system, it's warmed up, and now the chains can slide past each other. So you have more free volume, which means more room for energy to be stored, and therefore we have a larger heat capacity, which ends up being lower, further from zero on the graph that we have here. And we'll talk more about the glass transition and what happens when you're right at the glass transition when we talk about DMA. See if there's a question here.
Over here too.
Great.
Ellie,
Yes.
I forgot how high is the temperature this machine can?
We go up to 550. So one thing we want to be careful of though is we don't want to 550 degrees C.
Oh,
Yes.
fair.
C, Celsius. So one thing we want to be careful of when doing DSC is we don't want to degrade your polymer so much that it's going to turn into a gas inside the DSC, because then it's going to coat the DSC cell and contaminate it, and it's a pain to clean. So we typically heat up for organic materials to about 220. Is usually a pretty safe material for most hydrocarbon type materials. But we can go to 550 for materials that are safe to run up to 550.
PMMA and the polycarbonate.
Yeah, so some more stable polymers we can heat up a little bit higher. And if we don't know, we'll do TGA first. So in general, if you want to heat past 220, I'll have you do TGA first so you can prove that your material is stable up to the temperature that you want to run to in the DSC.
Thank you.
Yeah.
I have a quick question about the uniformity of the balls. Because like I'm guessing they're like the same material, so there's like layers to it, but then why is it like only the surface is like soft and like you can't really like go through it?
So they are both homogeneous. There's no layers, it's all one material, and we can kind of see that via the FTIR in particular, is that we see a difference in their chemical functionality. So they're not the same material we've found so far. So as you squeeze harder, that's kind of a frequency dependent response. And we'll talk more about that when we talk about DMA. So if you squeeze fast, it will feel stiffer. And that's true of many viscoelastic polymers. And then as you squeeze more and more, you get out of what's called the linear viscoelastic region, which we're going to talk about. So you can see an increase in stiffness. If you have a rubber and you start squeezing it, first little bit is easy, and then it gets stronger and stronger. That's because of what's called the linear viscoelastic region is that first part, and then we're getting nonlinear effects as we squeeze more.
Thanks, David. Thank you.
You're welcome. And there was a question in the chat, why not cool first, then apply heat? So if we cool first, we can cool first and then do a heat-cooled heat. That's perfectly fine to do. The purpose of that first heating cycle is to erase the thermal history. So just by cooling, that generally won't melt crystallites or otherwise erase the thermal history. When talking about thermal history, that means kind of what degree of crystallinity you have, how many physical crosslinks do you have, all things that are going to kind of remain the same as we cool. But as we heat up, then we give it more energy to the system, and then things can start to change. So if we take energy away by cooling, it's not really going to change the system very much. We need to put energy in to make something happen. All right. So comparing the two curves, we can see they're quite different. Interestingly, we see that there is one peak that they have in common. So these are not completely different materials. There's some commonality between them. And we saw that also in the FTIR. They had very similar CH peaks. One had a little bit more high energy CH. Next, we'll talk about DMA. And this is where we kind of get into the heart of the mechanical analysis. So DMA is dynamic mechanical analysis. It works by a load cell that's going to oscillate a piston in the middle here. And we can do it in compression, tension, three-point bending, a variety of modes I'll show you in the next slide. And it's going to create an oscillating deformation on your material. So traditional mechanical analysis would be just an Instron universal tester where you can just pull the material apart or just push it together. But that's only really good for very elastic materials, purely elastic materials. So if I push on this table, the harder I push, the more it deforms. That's Young's modulus, that's elastic. If you go to the ocean and put your arm through the ocean, it's not the amount of force isn't proportional to how far you go. What dictates the resistance your hand feels? So if I go like this, or I go like this, I can get to different locations, but what's dictating kind of how much force I have to put in? Viscosity, did I hear? Yeah. And the rate, yes, exactly. So it's the rate at which we apply that force. So for Young's modulus, it's how much force, but for viscosity and what we call loss modulus when looking at polymers, it's the rate at which that force was applied. So by doing this oscillating motion, we have a range of strains, a range of stresses, and then also a range of rates. So we can pull all those apart to get both the elastic component, which we call the storage modulus, and the lossy component, the viscous component, which we call the loss modulus. So it's great for characterizing materials that have both viscous components and elastic components. And almost all biological materials have both. Most, if not all, polymers have both. So this is, in general, just a better way to do a mechanical analysis as opposed to like an Instron where you just get the Young's modulus. As I was saying, we can do a variety of deformation modes. So we can do a three-point bending for stiffer materials, or clamped bending, or clamped three-point bending, or tension or compression. So tension for fibers or films, compression if you have some block of material. And we can also do shear on here. We also have a rheometer, which can do shear measurements for solids and liquids. And this is what all the geometries look like actually in the system. It's very modular, which is nice. It means there's lots of little parts to swap out, but I can assist you with that. So you can use the deformation mode that's most appropriate for your material. So we have this oscillating stress and oscillating strain. And for a purely elastic material, how do you think these curves should line up? Should they be offset? Should they be kind of all together? What's the relationship between stress and strain for purely elastic? So if I take a piece of this table and put it in the DMA, how is the relationship between stress and strain going to be? Complete overlap, exactly. So if we have a purely elastic material, the more we have stress, the more we have strain, and vice versa, and they're always going to go together. If we have something that's a pure liquid, we can't put pure liquids in the DMA, we can put them in the rheometer, which operates similarly. But if you have something that's purely liquid, we're going to get this actually perfectly out of phase because of the way that the strain rate and the motion of the material is going. For viscoelastic materials, we get something in between, which is interesting, and that's how we get the data. So we get an offset between stress and strain called delta. This is also the angle. We call this the loss modulus E double prime, and this is the storage modulus E prime. So this is the lossy component. This is the storage component. And we can think of the tangent of delta is opposite over adjacent. So E double prime over E prime, loss divided by storage. So we can say, okay, if we have a large delta, we have a large E double prime relative to E prime, we have a high loss modulus, and vice versa. So we can get some data for these two rubber balls, and we can do an amplitude sweep first. So this is as you push more into the ball, how does it respond? This is exactly to your point earlier. So if we have kind of small amplitudes up to about 10 microns that we're indenting on the sample, we get pretty consistent moduli. It feels about the same in terms of how stiff it is. As we start to go up to 100 microns, then we see, okay, all of a sudden it takes a lot more force. It's a lot stiffer of a material in terms of the storage modulus. So this is what's called an amplitude sweep. This is what we do first. We generally want to measure in the region where we have consistent modulus over a range of amplitudes. That's what's called the linear viscoelastic region. What's happening there is the chains are pushing together and then springing back to their original conformation. We're not doing any permanent deformation on the material. Once we get past that, then we start to break bonds or break chains, or change our physical crosslinks, and then we're doing some actual change to the material. We're out of the linear viscoelastic region. We're really starting to deform the sample. And that's not, then we're not characterizing the sample, we're kind of characterizing our measurement. So we want to stay in this linear viscoelastic region. So this is comparing the storage moduli. We can compare the loss moduli on its own. We can compare our loss moduli up here in the top right, and we see a much higher loss modulus all across different frequencies for the sad ball. And then we see a change in the loss modulus, or in the storage modulus, as a function of frequency for the sad ball, while the happy ball has a consistent response. So what that means is, so if you push quickly or slowly on the happy ball, it's always going to feel about the same. If you push quickly or slowly on the sad ball, it's going to feel much different. So we get much higher resistance if we squeeze quickly on the sad ball, and much lower resistance if we squeeze more slowly. So you can keep passing these around in case anybody wants to try any of these things that I'm talking about. So back to our triangle over here with our delta, we see E star, that's our hypotenuse. That's kind of the total mechanical properties of the material, the total resistance to deformation. So the complex modulus is just the triangle like that, Pythagorean theorem. And we can plot the complex modulus as well. So we see overall, we see this trend as we squeeze faster for the sad ball, it becomes much stiffer, where it doesn't really matter how fast we squeeze for the happy ball. It always feels about the same. We can then do a temperature sweep and say, okay, given just one amplitude and one frequency, we're going to sweep our temperature and see how the material responds as a function of temperature. So the storage modulus, we see that above negative 40 degrees or so, the happy ball is pretty consistent, but below that, it becomes much stiffer. So what do you think this is? Thinking about the DSC data. So what type of transition? Okay. So this is our glass transition here. So this it's in the rubbery state from about negative 25 and higher, and it's in a glassy state at negative 50 and lower. So if you cool that ball down, put it in liquid nitrogen for a while, it's going to be glassy like a ping pong ball. And almost all polymers will have some glass transition temperature, above which they're rubbery and below which they're glassy. For the sad ball, we see that the actual glass transition temperature is right around 15 degrees Celsius, which is close to room temp. So when we're bouncing it, it's kind of at its glass transition point. And that's the key for why it has some different mechanical properties. We can also look at the loss modulus, and we see a peak in the loss modulus right around, again, the same temperature, that glass transition temperature. We see a peak in the loss modulus for the happy ball, again, at its glass transition temperature. Finally, we can look at the ratio between the two, look at the tangent of delta, and this is basically how much is it lossy relative to elastic. And we see a peak, again, negative 50-ish for the happy ball, and right around room temperature for the sad ball. So this is why the sad ball does not bounce. If it was glassy, it would bounce. If it's rubbery, it'll bounce. But at its glass transition temperature, it does not bounce. So if we heated that up to, say, 100 degrees, it's going to bounce just like the rubber ball. So it's not just the material, it's the temperature at which the material is being used. So what's happening at the molecular level? So glassy, chains locked in, rubbery apart. Right at that glass transition temperature, there's enough free volume for the chains to slide past each other, but then they don't spring back. And that's why the ball doesn't bounce. We can also look at this. So DMA is a pretty traditional method of looking at polymers. We now have nice atomic force microscopes, AFMs, that can basically indent on your sample, and we can do mechanical property mapping at the nanoscale. And I'll show you some data for the happy and sad ball with the AFM. How are we doing on time? All right, great. So the AFM is a more complex instrument. We're going to have a cantilever that's going to indent on your sample. We're going to align the laser so it bounces off the back of the cantilever and then hits a detector so we can see exactly where the cantilever is. And we want to have, so as the cantilever moves up and down, as it pushes into the sample, the laser spot on the detector is going to move. And for us, we're going to be doing force spectroscopy, where we push into the sample at many points. We also have other AFMs in CNS, one that are either intermittent contact or what's called AC tapping or contact mode. So if you just want the topography, these modes are a little bit easier. But if you want topography and mechanical properties, the force spectroscopy is really the best bet for you. We need to make sure that we indent just a little bit into the sample. If the cantilever is too soft, it just sits on the sample surface. If it's too hard, it just kind of stabs through your sample. So matching the cantilever is very important. That's what this slide's all about. We can have sharp probes that have a very sharp tip. These are more traditional AFM probes. So these are good for indenting into some stiffer materials. If you have soft materials like lots of biological tissue, hydrogels, et cetera, you might need a more broad probe where we're distributing that force over a larger area, which is less of a strain on the sample. But depending on what material you have, you'll need to choose an appropriate cantilever to get good data. This is what the software looks like and kind of the interface for that. So we have our cantilever here. We're going to place the laser, which is this little pink spot, onto the end of the cantilever so we can monitor its location. And then we're going to align so the reflected light bouncing off that cantilever is exactly in the middle of our detector and that we're getting good signal with the blue bar on the right. We're going to oscillate that cantilever in air and look at its response, its frequency response. And from that, we can back out the calculations for the sensitivity, which is how much the probe is moving up and down, and the spring constant, which is how stiff the cantilever is. Thank you. Then we'll start acquiring some data. So for each point on this image, we're going to have a force curve that looks like this. So we're going to get hundreds, if not generally thousands of force curves, and then we'll average them to find the mechanical properties of the sample. And we can also look at heterogeneity. So if you have, say, some biological tissue where part has a tumor and part does not, we can see the stiffness of the tumor and that interface between the tumor and the healthy tissue. We can look at bacteria, cells. I've looked at lung tissue, kidneys, teeth, not liquid crystals, but crystals of various kinds. Basically anything that we can fit under the AFM head, we can characterize its mechanical properties at a very precise length scale. So we get some data that looks like this. We're going to process all of those force curves. We're going to fit with what's called the Hertz model, and that's going to give us a modulus for that particular force curve. And then we'll apply that processing to all the force curves. And then we finally get some data out. So this is just the height profile of the happy ball and the sad ball. So there's 10 square microns on each one. And we see just kind of what the morphology looks like down at the nanoscale. So this is a much higher resolution than we saw with the optical profilometer, but we can see kind of what's happening at the scale. Additionally, for biology, looking at this scale is especially important because this is the scale that cells are going to interact with your material at. So if you have some tissue that you want to grow more cells on, you want to know kind of what the topography is and also what the stiffness is at that length scale, where the DMA is just a bulk measurement. This is a very surface sensitive measurement. So in biology, we're often dealing with lots of surfaces. So we want to know what's happening at the surface. And then finally, we get our mechanical property mapping. We see the happy ball is pretty uniform. We don't get much variation across the whole surface. It looks like just a very homogeneous material, very homogeneous stiffness. And there's a question that I will get to in just a moment about the Hertz model and another question about DMA. We'll get to those in just a moment. So for the happy ball, we have a very homogeneous surface. Interestingly, for the sad ball, and this is where we really can start to learn about both the chemical and physical properties of it, is we see some stiff regions and also some soft regions. So for me, this tells us that we have kind of maybe two different materials present, one soft material and one stiff material. So the sad ball, the happy ball is a cross-linked polybutadiene. So all polybutadiene cross-linked with sulfur vulcanization, and that just makes a standard rubber bouncy ball. The sad ball's what's called styrene butadiene rubber. It's a copolymer. So there's two different functional groups present in terms of the polymer chain, side chains. And one is much stiffer than the other. And that's what allows us to have, we can tune our glass transition temperature based on the ratio of those two polymers that are present. So this is how tires are made. So you want your tires to absorb shock from the road. You don't want to be bouncing down the road over every frost heave as much as you can help it. So the sad ball actually has much more applications. You can tune shoes this way as well. So if you want some track running shoes, you want as much rebound as possible. If you want a long distance running shoe, you want to absorb some of that impact. And then you can mix in a little bit of copolymer and many applications of anything that kind of moves around the earth. There's going to be some mechanical forces that are being applied. We have to think about how to optimize those forces and the response of the materials. So other instrumentation that we have that I didn't cover today, we have a rheometer, which is very similar to the DMA. We do an oscillatory measurement, but typically in shear. And that's great for kind of things that are more liquid-like, softer gels. The DMA is better on kind of slightly harder gels, stiffer gels and plastics. We have a Raman microscope, which you heard a lot about last week. So there's one in this lab as well. We have a 325, a 532, and a 785 nanometer laser on this system. So the 785 is great for biological material. NMR, if you're doing any chemistry, we can look at what molecule you have. Nanoindenter is similar to the AFM, but it's better for stiffer materials like ceramics, metals, etc. The AFM kind of tops out around 1 gigapascal, maybe 10 gigapascal, so we can go up to like hard plastics. If you have anything harder than that, then the nanoindenter is a good option. We have a tensiometer, so looking at surface energy and also contact angle on a surface. Zeta sizer for looking at particle sizes, kind of 2,000 nanometers or below. That can be a lipid, a protein, an inorganic particle, metal, etc. Any type of particle that you can suspend in a solvent, we can look at via the Zeta sizer. And a probe station for electrical characterization. So if you're making any devices, solar cells, transistors, it's also good for looking at dielectric constant. So we can do kind of similar to electrochemical impedance spectroscopy with the probe station. Anything where you have some electrons flying around, we can usually characterize that in some way using the probe station. So I'm not going to read through all of this again, but you can take a look at the slide. Let me know if you have any questions. Yeah, think critically about what materials, how you want your materials to behave, and then what type of characterization might help you understand that behavior. And it's always good to look at the literature, see what other people are doing on similar materials. We probably have similar instrumentation here somewhere in CNS. So be like, oh, that's cool science. I want to do something similar. Talk to CNS staff. We're here to help you. Yeah, and don't be afraid to reach out. So I'm happy to take any more questions, and we can take a look at the lab for anyone who is interested. It was just down the hall. Thanks. Yeah, question. And I'll get to the chat questions in a moment. Yes.
Otherwise, it's completely transparent.
So completely transparent is okay. Diffracting properties, depending on the thickness, can be an issue. So if we're going to have light that reflects off the substrate and then does some weird diffraction as it comes back up, so typically a very thin film, like 300 nanometers or less, then the AFM is probably a better characterization technique for the surface. If you have a thicker film or just a transparent film that's, again, thicker, then it's perfectly fine. So the transparency is not an issue, it's the diffraction that is. Yeah, Sarah.
Really cool talk, thanks.
You're welcome.
When you were talking about the stiffness between tumor cells
Mhm.
and regular cells, what sort of sample prep do you need to be able to look at that? Can you look at tumors in paraffin, or what do you need to have?
Great question. So we need to have the surface exposed because we need the probe to push down. Additionally, we need a pretty thin sample. So the height needs to be less than a centimeter, often less than 7 millimeters. So sectioned tissue is generally good, and that's what people generally do. So if you want to like embed in paraffin and then section, that's ideal. We just need some exposed surface that we can push into. And we're typically pushing in about 100 to 200 nanometers, just for reference. So there are at least 2 questions in the chat, so I'm going to get to those. Does DMA exist for harder materials? So if you have a stiffer material, you can do a 3-point bending mode. So we can do metals with 3-point bending and characterize them that way. We won't be able to do compression or tension because we can only generate about 4 newtons on the DMA that we have. So keep that in mind. Well, if you have a stiffer material, it's usually purely elastic, and then people generally will just do a universal tester with an instron. Second question, and feel free to add any follow-up questions in the chat. Is the Hertz model really appropriate given that polymers show adhesion and the force curve showed that as well? That's an excellent question. So yes, the Hertz model just gives Young's modulus, which we've been talking about is not the best for polymers. So we do have the DMT model, which we can fit the retraction curve to look at adhesion for. Unfortunately, the Bruker software doesn't have like a JKR model or any of the other more advanced models. But if you do want to apply those models, you can export the data, export all those force curves, and then put them through Python or MATLAB or whatever software you want to do processing that way. It's just not built into the Bruker software. The Hertz model is what we generally see in the literature for most AFM data because it's the easiest. Again, it's not the most ideal model, but it's at least we can, if everyone's using the Hertz model, we can compare between different systems because everyone's using the same model, even if it isn't the most perfect model for those systems. Yeah.
What dimensional resolution can you get for the
For the FTIR, so for this FTIR is just you place your sample on the crystal and we don't get any dimensional information. If you want to scan across a surface, we have at least two options. So Raman microscopy gives a very similar type of data, looks at the vibrations of the bonds. So we can scan and map using Raman. That would be my first recommendation. We also have a reflection FTIR, which has a little bit lower lateral resolution, but you can also look around a surface, especially at a macro scale, to get data. Do you know, Arthur, off the top of your head, what the lateral resolution on the Lumos is? 10 micron, so still pretty good. With Raman, we can get down to half micron, but if 10 microns is good enough, you can consider the reflection FTIR too. Yeah. Yes, so glassy polymers, so ping pong ball is a good example of a glassy polymer. Polystyrene, so this tape dispenser, hard plastic, glassy polymers, hard plastics. In the hard plastics, the chains can't slide past each other. They have what are called physical crosslinks. So it's not that they're chemically bonded together, it's just that there's not volume for them to slide past each other. So when we push together for the ping pong ball, throw it at the ground, hit it with a ping pong paddle, it's going to just spring back. In a rubbery polymer, like the rubber ball, there's free volume, so the chains can slide past each other and slide back. If we're right at that glass transition temperature, they can slide past each other, but they don't really slide back. There's not enough free volume for that much motion to occur. And that's why it absorbs a lot of energy. And in this case, that ball doesn't bounce. Yeah. Any other questions? Any follow-up? Is that good? Okay. Yeah.
How long does it usually take to run the scanning calorimetry?
Yeah, great question. So we typically heat at about 10 degrees per minute and cool at 5 degrees per minute. So for a standard run, it's about an hour and a half usually. If we're heating up to like 200 and cooling back down to around 0, that'll be about an hour and a half. But you can do the calculation now if you want to heat up higher. Heat at 10, cool at 5, and then you have a heat, cool, heat. Yeah, hour and a half on average. Yeah.
What would be your recommended instrument for measuring the temperature profile of a polymer material that is sitting on top of metal, some sort of metal that is heating up, like essentially I think of like a transistor that's heating
So
up.
can you-
And I want to measure only the profile of the polymer layer, not the metal.
Right.
They're like separate.
Can you get the polymer on its own?
No, it sits on top of, it's manufactured.
It's manufactured that way? Okay,
not-
yeah. So depending on the conductivity of that underlayer, we could probably still do DSC because heating, assuming that that layer is not doing anything by heating up to 220, we would just heat up the whole system and you would still get a DSC trace. Your exact enthalpy values, so we calculate in like joules per gram, would not be quite accurate unless we can recalculate how much of the material was the polymer, but we can still see where the transitions occur. The temperature is going to be accurate. It's just the enthalpy of melting would not be accurate for a crystalline. But yeah, DSC, assuming, and again, the DSC pans are about 5 millimeters in diameter, so we would need to have a 5 millimeter circle sample to be able to put it into the DSC. Any other questions? All right, thanks all for coming. I can give a quick lab tour for people who are interested, and otherwise we'll see you next week.